In this segment, we're going to look at one of the most important tasks performed by an operating system, which is process scheduling. So, in one of the previous segments, we looked at what a process is, and we also saw this diagram which depicts the various states of a process. Now, when a process is in the ready state, and if you are not familiar with what a process is or what this diagram talks about, I would encourage you to pause at this point, go back to the previous segments, watch that and come back. So assuming you are familiar with processes and process states, now if a process is ready for execution, it is put in something called a queue. Again, we saw different types of queues, the ready queue, input output queue, and so on and so forth. So when a process is ready, it is put in the ready queue, and it is the operating system's job to look at the ready queue, look at the various processes inside it, and pick out one process at a time and assign it to the processor. So if you have multiple CPUs, if it's a multi-programming system, then your OS is going to pick out one process and assign it to each CPU. And if it is a single core system, then even for that one core, when you have multiple processes, you have to decide the sequence in which they get executed, right? So that is decided by the CPU. So the task of assigning a process to the processor and hence deciding which process goes to which processor or which order the processes get executed in is what we mean by process scheduling, and this is done by the operating system. This is one of the most important functions of an operating system. So to do this scheduling, we have different algorithms. So there are different criterion by which you can decide the sequence in which processes get executed. First come, first serve, shortest job first, earliest deadline first, round robin. There are plenty of such algorithms, some of which we will be looking at in detail. So the choice of algorithm, of course, depends on the OS architecture, and each algorithm has its own pros and cons, which we will be looking at in the subsequent segments. So the key takeaway here being process scheduling is where the OS picks up a process and allocates it to a processor, and in that by virtue of that, it decides which sequence the processes get executed in. So before we go to the actual scheduling algorithms, there are a few technical terms which we need to be familiar with. Your scheduling algorithms can be broadly classified as preemptive and non-preemptive. So I would like to start with non-preemptive first. So non-preemptive scheduling refers to all those algorithms wherein once a process is allocated to the CPU, a context switch happens only after the process has completed execution. So the definition given in the slide is a slightly more intricate, nuanced one, but the core meaning is once a process has been assigned to a processor, the processor will let go of that process only after its execution has been fully completed. So if there is an interrupt in between, or if the process has been running for an extended duration of time, or if some other more important process is waiting, that is not going to cause the processor to put this current process on hold and take something else up in a non-preemptive scheduling algorithm. So once a task has been taken up, the task needs to be completely finished before the processor will move on to the next task. So that is what we mean by non-preemptive scheduling algorithm. So your first come first served is an example of this. Shortest job first is an example of this. Earliest deadline is an example of this. We will be looking at these algorithms in detail in the subsequent segments. And when I explain an algorithm, I will also tell you why it is preemptive or why it is not preemptive. So if the terms don't make sense right now, there's no need to worry. What I want you to know is when I say non-preemptive, I mean that a process once taken up will not be switched for another process until and unless this process has been completed. That's about non-preemptive. Now we move to preemptive, which is the opposite. So obviously some context switch is taking place in between also. So context switch again was discussed in one of the previous segments, but if you don't remember or if you're not familiar, when one process is leaving the processor and another process is being taken up, the CPU has to relieve itself of the information, the data corresponding to the old process, and instead it has to take up the information, the instructions, the program counter and all that corresponding to the new process. So that switch is what we call the context switch. So I've explained that in a little more detail in one of the previous segments again. So if you think you need to brush up, I would recommend that you pause at this point, revisit that segment and then come back here. So assuming you are familiar with context switch, preemptive scheduling is where a context switch happens midway. So I assume the processor has taken up a process P1. Even though P1 might not have been completely executed, at some point it is possible that the processor will pause P1 midway and take up some other P2 or P3. It could be because there was an interrupt, or when the time slice expires. This round robin is an example of preemptive scheduling where this time slice thing happens. Again, we'll talk about round robin in detail soon. Or when a more important process arrives, this process will be put on hold and that will be taken up. That will first be completed and then this will be taken up. So when the processor is ready to abandon a job midway temporarily, take up another job, finish it and then come back to the old job, we call it preemptive. If that is not allowed, if the processor is going to finish a task at all costs before moving to the next task, we call it non-preemptive. And the dispatcher is that component of the CPU which aids in the scheduling process. So this is what helps in performing the context switch. So removing this data from the CPU, the current process's data from the CPU and putting it on the process control block, picking up the next process's data from its PCB and putting it on the CPU, switching between user mode, kernel mode, all of that is done by the dispatcher. So that is a component of the CPU which aids in scheduling. So that is some basic introduction to scheduling and some of the terminology associated with that. So with that out of the way, we will now be moving on to different scheduling algorithms.